Hello, today we are going to learn integral test. In this section, we have one definition that explains what the integral test is. First of all, we learn the definition, and then we solve few problems. Integral test. This is the definition that we're going to learn. If f of x is a continuous positive decreasing function on 1 comma infinity and let an equals f of n, that is the first term, nth term, then if integration from 1 to infinity f of x dx is convergent, then sigma n goes from 1 to infinity an is convergent. If integration from 1 to infinity f of x dx is divergent, then sigma n goes from 1 to infinity an is divergent. Alright, so let me explain this. Let's say you have a function f of x which is continuous, positive and decreasing. Let me draw that function. So you have a continuous, positive and decreasing. So the shape should look like this. This is a continuous, decreasing and positive function. Here you have x. It is from 1 to infinity. Let's say this is 1. Let me make a small change. That is 1. Then what is given here is if the integration of this function is convergent, the integration of this function from 1 to infinity is convergent, then this series is convergent. Actually, this series is given by that, which is an equals f of n. All right. So this is 1. This is 1. Then here you have f of, let me use blue. Here you have f of 1 which equals a1, and let's say this is 2. Here you have f of 2 which is a2 and so on. Let's say this is 3 and then this is f of 3 which equals a 3, like that, right? So this explains a nice relationship between the series and the function. All right, so this is the integral test. You can understand this test once you do a problem. Let's move to problem solving. And let's move to the first example. Example number 1. You have to find this series is convergent or divergent. Okay, you have to check whether this is convergent or divergent. Here, this equation is so important. By using this important, you can get the corresponding function. Okay, first you have to find an, and then you have to just take that as the function f of n. All right, so find an here. An is the n term which is right here. This is an is 1 over n, and then actually this equals the function. That equals the function. Okay, that's f of n as explained here. As explained here, it is the function. An equals f of n. Since you are familiar with using x as the independent of a function, since you are familiar with using x as the independent variable of function, I will just take it as f of x equals 1 over x. Okay, so these are same. Here 1 over n, here 1 over x. That's I just change n to x for convenience. Okay, so now you got the corresponding function, and then this function is defined in this function is defined in the interval 1 to infinity. Okay, that's defined. This function is defined from 1 to infinity. And then you have to consider whether f of x is decreasing, continuous, and positive. Right? So it is clear that f of x is continuous let me take this here. Continuous, positive, and decreasing. Okay, you have to check all these three conditions. Okay, it should be continuous, positive, and again decreasing. Okay, so everything is satisfied. It is continuous, positive, decreasing. You know, this function is very familiar to you. If I draw the shape of the function, it should look like this. The function should look like this. You have drawn these functions in Calc 1. So this function goes like that. F of x equals 1 over x. All right. Now let me just take some space here and take this graph right here. Now it's clear to you. All right. All right. Now, according to this definition, you have to get the integration of this part. You have to integrate f of x with respect to x from 1 to infinity. If it is convergent, this series is also convergent. So that's the routing that we follow. So I'm going to integrate this. Integrate from 1 to infinity f of x. Okay, so that is integration 1 to infinity 1 over x. As you remember, since you have infinity as the upper limit, you have to use the techniques of you have to use a specific technique here. You can't just integrate while having infinity. All right. So we learned this one in one of early section. The approach here is you write this integral as from 1 to some value b, and then you write limit this b goes to infinity. You learned this one in one of the previous section. Okay, because you can't integrate with infinity. Let me write that. You can't integrate with infinity. Because of that reason, you just use this trick. You just integrate from 1 to b, and then you say b goes to infinity. Okay, now do the integration. This equals limit b goes to infinity. This is ln x from 1 to b. Okay, this equals limit b goes to infinity ln b minus ln 1. As you know, ln 1 is 0. Now it is limit b goes to infinity ln b, which is infinity. The answer is infinity. Now the integral was infinity, that is divergent. The integral was divergent because this integral was divergent. Then the conclusion is the series divergent too. Okay, then the conclusion is series divergent too. Let me write that down. Since integration from 1 to infinity f of x, this is divergent. Since is divergent, this series n goes from 1 to infinity 1 over n is divergent. So let me write just let me write 1 over x here, because f of x is 1 over x. Here f of x is 1 over x. Let me move to the next example. Now it is example number 2. This is the given problem. In sigma n goes from 1 to infinity n e to the power negative n square converges or diverges. Okay, you have to check whether this is convergent or divergent. Alright, so again you have to find the corresponding function. First of all, you have to find the nth term, which is an. An is actually e to the power negative n square, and then you have to convert this one to the corresponding function, which is f of x equals, just replace n by x e negative x square. Alright, this x varies from 1 to infinity. Alright, and then you have to find if is continuous, whether it is positive, and whether it is decreasing. Alright, so first you can see if this function is continuous. Fx is continuous since x and e to the power negative x square are continuous. Alright, the first point is checked, it is continuous. And the next thing is, give me a second. And the next point is you have to check it is positive. Yes, it is positive. Why? Because each function is positive. The f of x is positive since x is let me write like this. Since x and e to the power negative x square are positive in the region is x in 1 to infinity. Okay, then third one, you have to check whether the function decreases or not. Does f of x decrease? Okay, so how do you check whether a function is decreasing or not? For that, you could use the first derivative that you learn in Calc 1. Let me compute the first derivative of f. Okay, so this is f prime x. Let me write it again. F prime x. Alright, so just compute the first derivative of f of x, then it is x, and then the derivative of e to the power negative x square, and then plus e to the power negative x square, derivative of x. This is the multiplication rule for differentiation. Okay, so this is x times the differentiation of that is actually e negative x square, and then use the chain rule to get the derivative of the power, which is d over dx negative x square, and this is e to the power negative x square times 1. This is x e negative x square, the derivative of that one is 2x plus e to the power negative x e to the power negative x square. Now you can see e to the power negative x square is a common term. You take e to the power negative x square out, and then you write 1 minus 2x square. Okay, now this is f prime x. You computed f prime x. Now you have to check whether f prime x is negative or positive. Okay, if this is negative, it is a decreasing function, as you remember. If it is positive, it's an increasing function that you learn in Calc 1. All right, so let me write that down. Now you see this is always positive and that is always negative. Okay, the first part is always positive, then the second part is always negative. That means f prime x is negative. Okay, this function is negative in that domain. In x, let me write it like this. This is negative in x 1 comma infinity. All right, x is x is in the interval 1 comma infinity. So if prime x is negative, that is f prime x, sorry, fx decreases. I'm sorry, I made a mistake here. Decreases. All right, so your decreasing part is also done. So you have already shown f of x is continuous, then it is positive, and it is decreasing. Okay, all the three conditions are satisfied. The decreasing part is the hardest one because you have to get the first derivative and show the first derivative is negative. Show the first derivative is negative. So that will give you f of x is decreasing. That's what you learn in Calc 1. Okay, now you go to solve the problem. Now you're going to integrate x times e to the power negative x square. All right, so again you can't integrate this as it is because you have infinity as the upper limit. All right, infinity is the upper limit. Because of that reason you have to just use the previous trick that you learned already. So what you write is you write limit b goes to infinity and then write integration from 1 to b x e minus x to the power 2 dx. Okay, now you're going to get the integration of that part. Okay, let's get the integration of this part. Thereafter you just get the limit of b to infinity. Limit b goes to infinity. Here, how do you do this problem? As you remember, this is UV formula, integration by parts. All right, this is UV formula, integration by parts. Or maybe you could use the substitution rule too. The substitution rule is also applied here. Okay, let me use the substitution rule first. Okay, try, let me delete this. Try u equals x square. If u equals x square, then du over dx equals 2x. All right, and then you write this. First of all, let me take this as equation number 1. Okay, let me separately solve. Let me separately solve the integral part without the limit part. Yeah, I'm going to solve that separately. we're going to try that. Let me substitute everything. When x is 1, u should be 1. When x is b, u should be b squared. Okay, so now I have to adjust the limits too. Alright, then let me rewrite the problem. It is integration from 1 to b square x times e to the power negative u. For dx, I can just solve this for dx. Actually, dx equals du over 2x. This is du over 2x. Now you can see you can cancel this with that. And this equals half integration from 1 to b square e to the power negative u du. Okay, the integration of that one is half e to the power negative u divided by negative 1, and the limits of u are 1 from 1 to b square, and then you apply the limits, apply the upper limit e to the power negative b square. If you apply the lower limit, that is 1 over e. Alright, this is what you get once you solve this sub problem. Once you solve this sub problem, and then you can substitute this answer into equation number 1 to get whatever you want. Alright, so I'm going to plug that. Let me take this as equation number 2, which is the integral from 1 to b x times e to the power negative x square dx. Alright, then substitute 2 into 1. You substitute 2 into 1, and then you write integration from 1 to infinity x e negative x square dx. This should be limit b goes to infinity minus half e minus b square minus 1 over e. What I have done is simply substitution. It's a simple substitution. And then this equals, now I'm going to apply the limit. Let's say you just send b to infinity. If you send b to infinity, let me write this as minus half limit b goes to infinity to the power negative b square, and then this 1 over e does not change because that's independent of b. Okay, this goes to 0 when b goes to infinity. This goes to 0. So the solution here is 1 over e, negative 1 over e. That means the integral is finite. Okay, the integral is finite. That means this thing converges. Integration from 1 to infinity x e to the power negative x square dx converges. Since that converges by using the integral test, let's go back to the integral test. If this converges, then you could say the corresponding series convergent too. Okay, so you are using that feature. Thus, the corresponding series sigma n goes from 1 to infinity, n e minus n square converges. Alright, so that is the solution. Now we are moving to the third example. Before moving to the third example, I would like to give you a special note. This note is about P series. This is a very special note. I will just write it in red color. Special note. This special note say you wanna integrate 1 over x to the power p from 1 to infinity. Let's say you want to integrate that. Okay, this integration is either minus 1 over 1 minus p. P is greater than 1, and or this will be infinity if p is greater than or equal to 1. There are two cases. The first case is p greater than 1. If it is p greater than 1, then this integral is actually minus 1 over 1 minus p. If p is smaller than or equal to 1, then this integral is actually infinity. Okay, that means this is finite, this is infinite. Okay, finite and infinite. Those are the two cases. Let me write the two cases. This is the case where it is finite. This is the case where it is infinite. Okay, now let's go to the example number 3. For what values of p the series which is right here the series sigma n goes from 1 to infinity, 1 over n to the power phi converges. Okay, so this is the given problem. First of all, you have to find the nth term. So that's the nth term. So you write an equals 1 over n to the power p, and then you find the corresponding function, which is f of x, which is 1 over x to the power p. All right, now you have to get the integration of this, integration from 1 to infinity f of x dx, which is integration from 1 to infinity 1 over x to the power p dx. Okay, this integration is given right here, which is right here. So it's an easy problem because this integration is given as a special note. Then this integration is actually minus 1 over 1 minus p if p is greater than 1. This is infinity if p is smaller than or equal to 1. Okay, so these are the two cases we have. These are the two cases we have. Then what happened? This is the finite case. This is the finite case. This is the infinite case. That means finite means this is the convergent case, convergent. This is the divergent case. Okay, so finite means convergent, infinite means divergent. So integration from 1 to infinity, 1 over x to the power of p is convergent when p is greater than 1. Alright, that is, this series n goes from 1 to infinity, 1 over n to the power p is convergent when p is greater than 1. So that is the solution. Okay. For this solution, actually you got help from the special note. This is special note is very important. The derivation of this result is not required for your class. Okay, the derivation of this result takes a lot of time. All right, so let me. So this is the end of the section where we learn integral test. We discussed 3 good problems. This is the first problem that we discussed. Here we have the series as the series here is sigma n goes from 1 to infinity, 1 over n, and that series was divergent. And then we move to the next example, which is right here, and that series was convergent. And finally we move to the last problem where the series was convergent again. All right, so that's the end of the section. Thank you.